Hello. This is Fuzzing Bootcamp by VRig. I'm Aleksi. I'm a third year, and I am the lead of VRig, and this is.
It's Tanush, another lead of VRig, and we're going over fuzzing.
So this is just kind of like the agenda for today. I'm not really going to go over it, but yeah, I don't know. I don't think it's that important, right? Yeah, it's just the agenda. Okay, so what is fuzzing? Or I guess what is the point of fuzzing? The point of fuzzing is to find otherwise impossible, quote unquote impossible, to find bugs by basically just throwing like random or semi-random input at a program and waiting for a crash. Or I guess maybe hoping as well. Basically, you typically test anywhere from like thousands to millions of cases or inputs. And in like low level, for some background in like low level languages such as C, a crash usually like indicates that there's some sort of, or a crash will indicate that there's some sort of like memory corruption, which is potentially exploitable and interesting. AFL plus, or I guess on the second point here, American Fuzzy Lap or AFL has been the biggest innovation in like low level bug finding in recent years. When did it come out? 2013. So it's been a while, yeah. There's been a lot of improvements on top of it, but this is kind of just like a big, massive jump forward, or it was. Yeah. So before AFL, fuzzers were kind of, or they were often like quote unquote dumb and just threw random input or data like at a wall. So imagine you had like some sort of command line tool and you were just like echoing input like directly into it. That's basically what they were doing. AFL, on the other hand, is smart because of genetic algorithms. Essentially, AFL++ will mutate on and keep inputs that find new code paths or increase coverage. And that allows it to basically just like drill through like a program to find interesting code paths and exploit, or bugs, I guess. Yeah. So on the left here, there's like you have this diagram or little code snippet here. This is kind of what, or I guess it kind of shows like a big a problem here called like the nested problem, where like if we look at it, like I mentioned that previously, or the dumb fuzzer before AFL would have to guess or has a like 1 in 256 to the 5th chance of hitting that case 5, because it needs 5 consecutive like chars all in the correct order, and each char can have like 256 bits, so you get 256 to the 5th chance of guessing the input. That's never going to happen. So what coverage analysis does is that it will notice when the input starts with 1, so in that first if statement, and when it reaches that part of the code, it will save that input and then mutate off of it because it reached into a further path, into a further code path. Okay, I think that's everything on there. All right, this is kind of just like a bunch of, I guess, like industry fuzzers, right? Or popular fuzzers. AFL++, like I mentioned, is kind of like the industry. Oh, this is weird. Industry standard. Yeah, and libfl is also pretty good. It allows you to like build your own custom fuzzers. And this could be maybe more interesting if you were fuzzing like some non-standard targets, maybe like such as a kernel or embedded devices. Yeah, and then if you want to look at this on your own time, feel free. I don't think it's too important though for the rest of this. Okay, cool. So on here, we just kind of have a performance summary for when a bunch of these fuzzers were fuzzing libpcap, which is just like a packet capture library. And we can see that on the left here, AFL++ and Centipede, they had both over 3,000 or median branch coverage, so they perform the best. And then we see a big drop off here with Eclipser to AFL last. I don't know why that is. Are those real?
I think just mutation strategies aren't
Okay.
for it.
Okay, that's fair. Cool. And then we'll move on. There's nothing. It's not too important. Oh, was this on here?
Yeah.
Not on the. Did you? Hold up.
Oh, it's like a slide transition.
Oh, is it?
Yeah.
I didn't even see that. Okay. Cool. Whatever. My bad. Cool. So let's go over coverage-guided mutations. Essentially, coverage-guided mutations make modern fuzzers such as AFL++. It's how they are so effective. the fuzzers will learn which inputs are valuable, and then based on code paths that those inputs trigger. So the goal for this is to basically reach every one of these basic blocks on the image on the left here. Some background: a basic block is basically just like a straight sequence of code without any branching, so like no jumps or calls. So this would be like one basic block, you get another one here, and then you get like one here. These are all basic blocks. So basically your goal is to reach every single one of those basic blocks. The way it does this is that it will keep track of which edges or basic blocks of this graph have already been visited, and then if a new input hits in like unseen part of the graph, then that input is considered interesting because it reached a further part of the code base. Okay, so in the orange here, it's kind of highlighted. Describe it basically just like describes the logic for if AFL++ finds an interesting program, what it'll do when it saves it. So it calls a save if interesting, which we'll call like calculate new bits if necessary, that which will compare like the current execution path against like a global map of all the paths found so far. My bad. And then it'll look if it has any new bits, and if it does, then it will save that program to the input queue or the corpus. If it doesn't, it'll just continue. And then a bit tangentially, discover word is also there. Basically, the point of that is that fuzzers will often struggle to like get past like quote unquote like magic values or like hard-coded strings. So for example, if you had like a get or like a post somewhere in your binary or just some like random digit, it's not going to be easy for the fuzzer to discover those or get past. Yeah, know the correct input to get past. So basically, discover word will look for interesting like byte sequences in the interesting input, and if it finds like a potential word or like a sequence of bytes that's like a single unit, it will save it to like a dynamic dictionary from which like future mutations can splice these discovered words into like other inputs to hopefully mediate or alleviate the problem in the future. Yeah. Mutation strategies, I think they're at the middle here. They're just ways that a fuzzer can basically modify or mutate a given input. And fuzz level, another thing, is basically the number of times AFL++ has cycled through its input queue or corpus. Every single time it cycles, it will increase the havoc stage. And then when that gets incremented, actually, I'm not too sure. When it, that will, I guess the havoc stage, will determine, or it'll eventually cause the fuzzer to perform like many random or like high energy mutations all at once in hopes of trying to like find new edges. Do you want to add, do you know when they're like, when it's triggered actually? Is it just on every increment? I'm not too sure.
It's dependent. It's fine. It depends on the expiration point.
Yeah. Okay, cool. So here we have like three kind of main fuzzing modes. Excuse me. Standard function, like I mentioned earlier, basically you're just feeding raw data into a program. This is very slow because I/O and OS overhead, and starting and stopping a process thousands of times is not efficient. It's like rebooting your computer every time you want to like open a browser tab, for example. So the next improvement is forked server. Instead of restarting the program every single time, you use a fork server. Basically, you start the program once, you let it reach the entry point, and then you clone or fork the process in memory for new test cases. This is better because it skips like expensive overhead of like initialization and like loading libraries, for example. But it requires like the binaries to be instrumented, which is what the AFL Clang LTO and AFL Clang Fast are in the ++. And then finally, we have persistent mode, which is, I guess, arguably the best. It'll basically stop treating the program like a command line tool, so there's no more I/O. And instead, a harness will feed data directly into like a specific function or part of the binary that you want, without stopping the process. At least until a certain number of iterations have happened. So you have no more forking or restarting, so speeds can reach tens of thousands execs per second. It's a bit like wrong. You still fork, but not as often, or like barely. Yeah. Libfuzzer. This is an example right here, and then the next slide as well will be two examples of just persistent, what is it? Persistent like fuzzing modes for libfuzzer, and then the next slide is AFL++. Libfuzzer was on the previous slide, and it's an in-process coverage-guided fuzzer. So, like I mentioned, like traditionally a fuzzer has to fork and exec a new process for every single test case or input. However, this example and the next one show persistent mode. Yeah, okay. Basically, persistent mode will just keep the program alive and then feed new data in a loop. I think that's a bit more obvious on the next slide as well. Cool. So you kind of have like two main functions here. You have your LLVM fuzzer test one input, which is just the fuzz target or the function that the fuzzer is going to call repeatedly. And you have your data. It takes basically two inputs in the signature. You have your data, which contains like the mutated input generated by the fuzzer. As a note, it'll like always return 0 or -1. The other values are just like reserved. And then you have libfuzzer, or I guess, yeah, like I mentioned, libfuzzer will always look for the specific signature for LLVM test one input. And yeah, that's like required. You also have like LLVM fuzzer initialized. This is optional, and it just allows you to initialize like functions, or it's an initialization function that runs once when the fuzzer starts. So this could be useful for maybe you want to like load like a large like database into memory or set up some global states. You can do that there. On the document or on the docs, it was recommending not to do it unless you need access to argv or argc, but I don't know, probably not that deep. Yeah. All right. I think this is a better example in my opinion, just because it shows like the actual loop. But this is persistent mode for AFL++. Yeah. So I think the most important thing to take away from this is like all of the macros. So what we can see here is you have this AFL init, which will basically just like act as a checkpoint. So it'll tell the fuzzer like everything before this is like a one-time setup, and then to start like the actual cloning process here. So it doesn't have to clone. Well, it won't, I guess also, yeah, it won't clone on every iteration. I will get to that. We also have AFL fuzz test case buff, which will it's just a pointer to a shared memory region. So instead of reading from a file, AFL++ will like write test cases and like, I guess the program will read them from that shared memory region. And yeah. And then we actually have our main loop here in the while with the AFL loop. This is like the main loop. So every single time it loops, the fuzzer will like, I guess quote unquote like reset the program. It doesn't really. It'll just basically loop through it'll have one process and then just keep looping and calling this like LLVM fuzzer test one input int max times. And then once it reaches int max times, it'll refork. It does this so because like after maybe you have like a million iterations or however many int maxes, that's a lot. You'll probably inevitably have like memory leaks, even if your harness is written well. So it just like takes a preventative step to try and alleviate like false crashes. Yeah, and then test AFL fuzz test case length, which is like the test of the length of your input, and LLVM fuzzer test one input is, like I mentioned, like the target function or what you're actually testing. Yeah, here we also like used like the function signature from libfuzzer, which is like just like good practice. Yeah, and then one more thing I wanted to note is like the argc and like the argv up top. It's not really important, but they just like suppress compiler warnings. I just thought it was interesting. Yeah. Okay, I think that's everything on there. All right, cool. Writing good harnesses. This is very important. Let's just go over each one. So for the first one, you want to fuzz areas where the program takes in raw input or unstructured input, as this is where your program handles like untrusted like data. So think about like a network protocol parser, for example. By using like a coverage guided fuzzer and starting at like the top of the code flow, you can you'll basically just allow your fuzzer to discover interesting inputs and code paths. Cool. Also, depth versus breadth is pretty important. Universal harnesses are slow and like often get stuck in like shallow code paths. So creating small like focus harnesses allows you to reach better execs per second and like drill deeper into like your target code path. Then you also have cleaning up the programs, or I guess cleaning up the program's global state helps ensure that when the fuzzer reports a crash, it isn't just the harness crashing, but it's an actual legit bug. So over potentially like millions of iterations, memory leaks will cause your fuzzer to crash and report false positives. Yeah, so cleaning up the global state will help alleviate that, like I mentioned. I think this is only really necessary if you have like a global state as well, because ideally your like LLVM fuzzer test when input is like stateless, and that way it doesn't rely on any like external data. So it makes like the managing the states easier. Yeah, and then one more thing, like using LLVM fuzzer initialize to handle heavier tedious initialization steps that don't need to happen for every single execution. And then this will also just keep your fuzzer like fast and efficient. So I guess that's also like, yeah, just good practice. We have some more here. Basically, also, by not allowing your fuzzer, or not allowing for, basically you don't want to reuse multiple pieces of data, or the same piece of data as multiple parts of the data flow. And by not reusing a piece of data, or a piece of fuzzing data to be used as multiple parts of the data flow, you prevent like collateral constraints. I don't really know. Kind of AI slop, honestly, I'm not gonna lie. But imagine like a byte gets like used to identify, let's say like the length field, but it also gets used to identify like a type. Maybe there's like a type field as well. If the fuzzer mutates on that like single byte, then the length field might get like, or I guess if it mutates on that single byte to modify or mutate the type field, it'll end up breaking the length logic and prevent the fuzzer from reaching deeper code paths. And then also, each piece of fuzz data should map to one specific test scenario. I think it's a duplicate for number 2 here. It's just saying again, like clean up your global state to like help alleviate false positives and obviate real bugs as well. Okay, cool. And then debug output can significantly slow down your fuzzing. So remove like all debug statements basically when you actually want to do your campaign. Another thing is don't let your fuzzer waste time on garbage inputs that you already know will fail. So maybe there's like an input, or maybe your input is 0 bytes, but you know your target always requires at least 4. So instead, it helps to obviously like have good seeds or initial inputs, but you can also validate your inputs in a way that helps you reach your target code paths. Cool. Summarize your code. Okay. And then the last thing here, you just basically want to optimize your source code for your fuzzing environment. There's kind of like 2 main ways you can do this, is like stubbing out just a relevant code and like creating mock functions that return hard-coded results. For example, like if you wanted to like stub out some like math or like hashing algorithms when fuzzing like a parser, because you know those like algorithms or the math logic is just like irrelevant for the parser logic. Yeah. Almost through here. Is it? Oh, it is on the right. Is it? Oh, it is. Okay, my bad. Here, basically this is like just for like when you're like compiling your binaries in the fuzzer. You have kind of 3 different instrumentation levels with AFL++. AFL Clang LTO and AFL Clang LTO++. This is the fastest, or like the gold standard. It performs link time optimization, which will essentially just result in like slightly faster binaries that produce better coverage. And then we also have like AFL Clang Fast and Clang Fast++. These are still very fast, but and use a compiler plugin to instrument the binary. And then we have AFL GCC Fast and G++ Fast, and these are a good fallback for older systems or specific GCC like dependent projects. And then cool. And we'll go over environment variables, or sorry, environment flags, basically just like sanitizers. So while like the fuzzer might trigger a bug, if the program doesn't like actually crash in a way that the fuzzer notices, then the bug is missed. So sanitizers will instrument your code at compile time to detect bugs and vulnerabilities during runtime. They act as basically just like guardrails, watching your program execute and like catching problems that might normally be silent. So maybe for some reason you went out of bounds in an array, but it didn't actually like really do anything harmful, and your program doesn't crash. If your program doesn't crash, then the fuzzer's not gonna know that there's like a potential bug there. So that's where sanitizers come in. Essentially, they just add checks. For example, like around like a memory load or store, to achieve this. And then, yeah, these are just also just if you go back. I was just gonna mention, these are just kind of more for your reference. They're all like pretty cool and interesting, but I don't know. If you want to look at it on your own time, I think it's more efficient. And we have two more AFL. What do I have here? AFL TSAN and LSAN. I think libfuzzer has both of these enabled by default, and it's also important to note that some of these sanitizers like cannot be used together. For example, ASAN and MSAN, you can't use them together. So just like keeping that in mind is also helpful. Also, one more, the sanitizers tend to like trigger not trigger, slow down the fuzzer quite dramatically. So you might want to be like strategic with which ones you choose. And then finally, we have, or at least for this slide, we have input compiler avoidance tag. Basically, it's just like a macro. This like if, fuzzing build mode unsafe for production. This will basically just tell the fuzzer to not spend any time exploring like whatever is in those or like a certain code path. So imagine like if the code logic is checking like an HMAC or a digital signature that the fuzzer like will never be able to guess, then you can just kind of use this to always return like a valid signature. Yeah, you can basically just eliminate the need for the fuzzer to guess the correct checksum. Yeah, I think you also just like wrap your code in the if def and end if to achieve that. What?
I don't think I have time.
Oh. Maybe if we have time, we'll come back to the demos, but I think we're just going to skip them for now. And then, all right, cool. Tanush.
Yeah, okay. So the other part of this, one of the next interesting things that we want to talk about is the concept of making custom fuzzers and improving what a standard fuzzer does, right? So obviously programs are really complicated, and if you have a program that takes in like network traffic, like most of the time random bit mutations and bit operations aren't necessarily going to result in meaningful inputs. And let's say you kind of know the structure of your input style, or you have tags that you know, and you know the format of stuff, you can pre-make your fuzz input to actually be standardized to that input. And one of the systems for this is libafl. So libafl is a library for building custom fuzzers. It's made by the same team as AFL++. The main difference is it's in Rust, and now you're writing your fuzzer as well as then you have to write your own harnesses as well. So it's 2 layers, and it's kind of important to remember like the difference between these 2 layers. That'll come up in some time. But libafl has a bunch of powerful extensions and additions that make it very useful when you're fuzzing complicated targets. And I think it's important to also talk about selection process. So when you want to use AFL++ versus libafl, if you're trying to target a code base that's very highly audited and well tested, it's worth trying to create custom fuzzers and try to perform some level of optimization and innovation in terms of what the fuzzer's doing. So yeah. This section was like really heavy code analysis and kind of code explaining. We'll do it, but yeah, definitely worth looking to on your own. It's important to remember this is all in the context of writing your own fuzzers, and fuzzers are pretty complicated. So yeah. First of all, error handling and has metadata. So it's useful to actually keep track of error handling, because sometimes systems might crash in different ways. and you might actually, some errors might actually be interesting, and you might want to track stuff if it does error out in certain ways. So that's why you're given these primitives. Has metadata. Again, you might want to rewrite the entire metadata format for what you're keeping track of, right? An example of this is somebody wrote a fuzzer for a video game where they tried to fuzz the character movement. And again, it's genetic algorithms, genetic mutation. So the strategy here is after your character moves to an X or Y, Z point, you might want to keep additional metadata on the movement of the character throughout the map or something like that. So again, the idea here is that you're given so much control, you can do some very interesting things. Um, corpus. So corpus is where your test inputs are stored, and this is obviously like kind of the peanut butter and the PBJ sandwich, where it's like this is like really the most important aspect of your fuzzer in terms of this is what gets you the bugs, right? Um, what this allows you to do is you can do things such as like maybe writing to a database is something we actually did. No, not with libafl, but just something we did. As we start storing all of our test cases into a Postgres database, and that's just something you can do. It's just like changing where data is stored, how it's stored, how it's scheduled. Maybe you don't want to test all of your corpus inputs at once, or you want to schedule it in different ways. This allows you to do that. Yeah, let's go on to executors. So executors are kind of the idea of your LLVM fuzzer test input one. This is how, in terms of the actual fuzzer, and when you're building your own library or your own fuzzer, right? How the library sees it is it's seen as like a singular input. So there are different types of executors as well. And we kind of talked about that, right? The in-process executor, fork server, executor, in-process, fork executor. The main idea here, right, is you're allowed to define what is the start and end of an execution. So in-process executor, right, we're talking about the idea of, okay, we're going to keep spawning grandchild processes every single time after, say, 1,000 loops of the same input, right? Fork server, the idea is, okay, every time we have a new corpus, a new input case, test case, we want to fork the grandchild, and we want to keep all of this in the parent children processes shared memory region. And what you're allowed to do with executors now is you're able to essentially redefine what execution looks like, and you can create something like a fuzzer for a custom kernel or an operating system where your execution is actually starting starting QEMU and maybe tracking the QEMU states. And after QEMU finishes, you look at the inputs from the registers in QEMU and whatever, right? And executors essentially allow you to completely redefine what a process does, or the end to end of a process execution or test case. Um, breaking down generic process executors. Uh, The idea here is we have our harness. This is the function we actually are going to execute. Points to that, and then we're going to keep track of our execution counter. There are several global states and values that we care about. The most important things are pre-execution hooks, call to your target, post-execution, and cleanup of global states. And this is important because you're able to now define, say you want to do something before you execute a function, you're able to now create your own hooks to that. And maybe this is something on the, before you run, this was a good example. Let's say you want to store some level of metadata before you're going to execute a function, right, on a process or a server, right? Let's say you're fuzzing a custom server, it's written in C, and you want to save actually the inputs or what's stored on the website of the server. Let's say it's for like a IoT embedded router or whatever. And every time before you actually execute your target function, which is your harness function, right, you actually want to see what's on the website for whatever reason, right? You're able to do that. And then let's say you want to compare what's not on, or what's on the website after that execution. You can do that in your post-execution hooks, and I don't know. Let's say you want to clean something up, you also have the ability to do that with your clean global states. Yeah. Execution in librs. Um, okay. This kind of is how you're going to handle providing input to your harness. So you have your target, you have your buffer, and then your global variable libfuzzer test input 1. So this is going to actually send data, to your harness, get back to you, and then you're going to have your states, your instances, the event manager, the execution timeout. So all of this is like the result of that execution, and it's your executor, and you can continue to run the executor as indefinitely, obviously, as it goes with fuzzers. But the idea here is if you want to say change the format of the input buffer, right? This is kind of where the lines between a custom fuzzer and a harness sometimes get blurred, where your harness allows you to take in your input buffer and clean it up and maybe define it into some custom structure, and it's still garbage data in some ways, but you're now redefining it into a custom format. What you're able to do in the execution and the data here is you're now able to redefine the actual um, buff before it goes into your harness, where it might already follow a predefined format. So let's say you're going to be fuzzing elf headers, and you don't need, or sorry, elf files. You're fuzzing just elf files universally. Let's say you want to always have like your elf header format, and that's just something you can tack on to the very start of every buff. Yeah. Um. Yeah. Mutators. So mutators are a pretty important and interesting idea when it comes to fuzzing, because what mutators allow you to do is essentially define how you're going to mutate things and what mutation looks like. And I think we talk about this a little later, but we'll talk about some custom mutation strategies and mutators that exist that let you fuzz grammars. So if you've ever seen like a programming language, there's obviously like a definition for what the program language grammar is. So obviously every language and every program can be defined in some sort of like general abstraction, right? English, right? We always have a subject and a predicate, right? Subject and predicate? Okay. I'm pretty sure that's right, right? Subject and predicate. You always need those two things, and that's just like a format of an abstraction, right? Of a grammar. What can a subject be? Obviously, a shit ton of things. A human being, a name, a location, and a predicate can be all sorts of things as well, right? But the main idea is that you have this predefined grammar, and that's just a form of mutation. Let's say you want to mutate around those grammars instead of just arbitrary havoc mutations. And havoc, again, is just like bitwise, bit level mutations on the actual input buffer. But yeah, I don't know. This isn't that important to this talk, honestly. This is like more important if you're like really trying to get into the weeds of the internals for your fuzzer, but it's fine. Yeah, okay. Mutators in example code. Honestly, kind of explain this. This is fine as well. A lot of this has been shifted and stolen from a VRig talk that we did a while back. But yeah, so we can kind of see here in this example where in the actual source code of libafl this is actually happening, and this is kind of like helpful just to understand, I guess, the internals of the system. Uh, if it's confusing, you're also right, because you're writing the library in Rust, but your harness or your fuzzers are also in Rust. So two forms of Rust before you can actually do anything, I guess. But here we kind of see where our mutation happens, and what this allows you to do is change the mutator at like very low level if you want, right? If you want to make the mutator as custom as possible, where you're only mutating like certain tags, right? Let's say you have a list of like 100 tags that will exist. You can arbitrarily mutate on those if you want, and you can redefine mutator selection in this section of the code. Yeah, this is in librs. So we also had a demo for this. We're just not gonna do that. Yeah, so grammar and structure aware fuzzing. I kind of talked about this, and let's I guess talk about grammars for a second because they're kind of important, and some people might not fully understand how grammars work. The idea with the grammar, right, is you're abstractly defining what something can expand to is the best way of putting it. So you have your starts, and then that points to an expression. Well, what is an expression in math? Well, it's a term plus another possible expression. Okay, we already defined what an expression is. It's a term plus an expression. Okay, sure. What are term? A term, it can be a factor. A factor can be an integer can be a digit, and you have, say, 6 digits. Right? Or you have like a set constrained number of digits. In this case, they're actually just hard coding the digit to 6. But the idea here is we can define all the possible formats in a grammar. So let's say digit, right? Digit can equal 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or not 10, but 9. But yeah, so those are all of the possible values for your grammar. And when you're generating the definition of a language, your goal is to essentially describe all of the possible combinations for some kind of language or protocol. For example, something that I had to unfortunately read the grammar for was like the baseband custom dynamic or vector imaging system. So if you didn't know, and you probably shouldn't know, baseband towers actually have a custom dead imaging uh, format, and just this is honestly tangential. Who gives a shit? It's such a tangent. I'm sorry, but the idea is that like you have grammars and they allow you to define any language, and this kind of explains it. Kind of see the idea here is that you can keep defining terms and you can combine terms and you can generate all of the possible values. Why do we actually care about anything I just said? And it's not just like a insane man's yapping. The main reason is there is something called Nautilus grammar mutator. It's inbuilt into libfl, and the idea here is you can define your own custom grammars for something like, say, XML. And obviously, there's a lot of XML parsers, and XML parsers written in C might be bad because they can lead to bugs. A common trend in security and security research and vulnerabilities is that a lot of parsers are like pretty big no-nos because they're complicated, they're hard, and when you're parsing things that are like really complicated, like XML is not even that bad, but think what if you're like parsing like a programming language, there's non-trivial chance that there might be a bug in your custom parser. So something that's really useful for writing for writing for finding bugs is grammar fuzzing. And you are essentially, as you can see in kind of the image here, we're like making a custom grammar for XML. So we define our start, which is our document, and then XML and then document. And then we define what XML content can be, which is XML and then maybe more XML content. And then we define XML content as empty as well. And then we go ahead and define possible values for XML. So tag, adder, and maybe XML content again. And we kind of keep going down until we define a bunch of rules, and then we can keep adding things. And there's nice things in this library like regex. So if you want to define what the regex format for a specific grammar value is, you can do that. The main value here is you have syntactically correct inputs, which is like important if you're fuzzing like a programming language. And you might find better mistakes in the parser, but more than that, when you have a guarantee of syntactically correct inputs, you no longer need to, you can go past the input validation that formatting does, right? So if you're trying to fuzz a programming language, obviously the first thing that happens in any programming language or any compiler is it tries to validate that your syntax is correct, right? And if you have broken syntax, the code doesn't even compile. So that's not that useful a lot of times when you're fuzzing complicated targets like JS, JavaScript. And you actually want to guarantee syntactically correct inputs as best as possible. So grammar mutations are really useful for stuff like that. Yeah. So protobuf based mutations is kind of adjacent idea, and that's when you're like wanting when you want to fuzz say a protocol, and you know like the general format of a protocol, and you want to mutate the objects in a specific protocol and not just like arbitrary inputs. It's really useful for generating say like a here you see like message.proto, and you define what the message can be, and then you get to serialize that message to a string, parse from that string, and then you can send it out either into the fuzzer input or technically protobufs are used for a lot of things. But yeah, snapshot fuzzing. This is kind of okay. You can like go over these two things really quick. This is like another form of really advanced fuzzing, and we were kind of talking at it at the start when we were talking about writing our own custom executors. So the idea is that you're essentially now writing an executor to create a snapshot of a virtual machine. The executor, like, yeah, when you take a snapshot of a virtual machine, it's the same idea here. You're just going to take a snapshot of it before you start inputting values. And then as you input values, you're going to keep track of like the VM's internal registers and what it's doing and how it's doing. And you care about what the virtual machine state's like. And whenever it finds something interesting, you then save that new snapshot. And then maybe you do new mutations around that. And as you can see, it allows you to play literally Mario. You can fuzz Mario into existence and play the entire game of Mario by trying to calculate all the states. And you can define what, a new interesting value is. And in this case, it's Mario moving forward and not dying, right? This isn't perfect. There are issues with this, but it's a really efficient system for fuzzing complicated targets in two ways. You want to fuzz the Windows kernel, which is kind of black box, as well as Windows black box binaries. That allows you to fuzz targets like that, as well as allows you to say fuzz a network service where you redefine the entire Linux kernel's network stack. So the now it takes input from your custom fuzzer, which allows you to directly send inputs to the Linux kernel, and now you avoid having to write a harness really, and you can just use Nixnet and kind of win. Finally, we have like Frida fuzzing. Okay, this is like a tangent one, but whatever. Frida fuzzing is like the concept that hey, you have a Windows standalone binary, and you want to hook into, say, the starting of the Windows binary and execute that. And essentially, Frida is a tool that allows you to do this by dynamic analysis, and Frida's a really cool tool, and you can look into it, and there's a bunch there in terms of like shadow memory and keeping track of everything. But the main thing with Frida is it allows you to dynamically track and trace every binary. It's really good at it. And what this also means, it allows you to trace and track basic blocks, because it actually itself works on the basic block level. And so every time you get to a new basic block or you reach a new edge in your code coverage, you now can save that. And, same idea where you're now using that information to fuzz and send inputs using Frida itself as well. So twofold value with Frida. But yeah, all of this is kind of just built up to what our work was for the last like 3-4 months, where we got really into the weeds of a JavaScript compiler fuzzer called Fuzzily. And yeah, I'll let Aleksi take over for this bit.
All right. Just gonna kind of go over a high-level overview of the main points of what Fuzzily is and kind of like what it does. So I guess Fuzzily's like main goal is just generating interesting JavaScript code. However, because Fuzzily is targeting like core interpreter bugs, so think like on your browser you have something is running your JavaScript code on your browser. You're targeting that engine, for example, and that could be like a JIT compiler. Yeah. But doing so, it faces two kind of core problems. So you want to ensure these. You want to ensure. Sorry, what? Oh, sorry. You want to ensure syntactic correctness, and you also want to ensure semantic correctness. So syntactic correctness is just making sure that your JavaScript code that you generate is actually syntactically valid. The way Fuzzily does this is that it relies on its own internal like intermediary language called Fuzzing, which can only express syntactically valid JavaScript. So like in the example on the left here, it's missing a bunch of parentheses, so like in the function signature, in that for loop. Yeah, so that would not be syntactically valid. You also want to ensure semantic correctness. So essentially, this is any program that raises an uncaught exception is considered to be semantically incorrect or just simply invalid. So yeah. So in this example here, basically like what is the code doing is it's not doing what it's supposed. The code is not doing what it's basically supposed to be doing. So in this calculated average, we see that the syntax is fine, but it takes in these 3 values, but it just never divides by 3. So the actual semantics of that function are wrong, even though it's not going to actually error out. Yeah, so that one's a bit trickier, and they just left it up to each fuzzing engine. Cool. All right, FuzzIL, this is kind of like the bread and butter of Fuzzily. Essentially, like I mentioned, it's Fuzzily's own custom intermediary language, or IL, that mimics the JIT compiler's IL in various JavaScript engines. So maybe you have like V8 or JavaScript core. So Fuzzily, what it'll do is it'll exclusively operate on FuzzIL programs internally, and then only lifts them to JavaScript for execution. So that's kind of like in the top right here in the blue, just like that's basically it. It just generates the code, lifts it, and then executes it in the engine. Basically, this looks like a lot, but it's not too bad really. It's pretty like one-to-one actually. On the left here, this is an example of a FuzzIL program. It's basically just like a list of instructions. And if you see here, we have this like begin plain function definition and end plain function definition. So the begin is like the start of our function right here. And then we see that it's returning v0, which is our f0. And it takes in v1, v2, v3. So that's our 3 inputs right here. And then it does a binary operation on v1 and v2 and adds them and stores them in v4. So that's what this line is here. And then it just sets the property of v3, or the property called foo of v3 to v4. And then in the bottom here, similar. This is a one-to-one correlation, so v5 is v5. It loads that string hello world, loads this object, loads an int or float, and then calls f0 with those values. So yeah, that's what it would look like after. Cool. And then, it's the next slide, right? Did I miss one? Oh, I did. Whoops. Okay, cool. So yeah, this is kind of just some, I know they're not too relevant, but just examples or code snippets. So each program or the program class will like represent an immutable immutable unit of code, which various operations can be performed onto. That's the public let code. And then it also has a unique identifier. I think the comment says it can persist. I'm not actually sure if it can. It persists across like different fuzzer instances. I don't think it should be able to. And then since FuzzIL programs are immutable, when they are mutated, they're copied while mutations are like applied, which is done in Program Builder. Yeah. I don't think much of this code is very relevant to the actual mutations, but yeah, this is kind of like this is just 2 like big classes that are responsible. And then go to the next one. Yeah, cool. And then this is just kind of a list of like all of Fuzzily's like main mutators, or the mutations that it can perform on this FuzzIL. I'm not going to go over everyone, but I think some interesting ones are code or splicing. Basically, it'll just copy like a self-contained part of a program, or it could be even the whole program into another one in order to combine the features. And yeah, these runtime ones are also kind of interesting. They just rely on the fact that you have to run the JavaScript in the engine to get back runtime type information. And then based on whatever it's trying to do, for example, like probing, it might like use, probing will try to like determine what properties exist within an object, or I guess it's prototype. Yeah, and it needs the runtime type information to be able to like actually test out properties and see if those properties are valid within the object's prototype, or for that object. Yeah. I'll leave those there. I don't think there's much else on that slide. Yeah, this isn't too much either, but it's just kind of the base class for the mutator. So instruction mutator can mutate, and then the main function or the public func mutate, which will actually get overridden by the child class for the actual like implementation of the mutator. So that's what you kind of look for if you're like looking for the mutators in the code base. Cool. There's a bigger slide. Okay, so I'm just going to go over one of the engines that Fuzzily has. It has another one called Hybrid Engine, but I will just go over Mutation Engine because it's just like simpler, and I don't think it's completely relevant to go over hybrid for this presentation at least. So yeah, Mutation Engine is like the most basic type of engine that Fuzzily has. It'll essentially just perform n consecutive mutations on like a selected program and look for coverage or semantic errors. So that's what it's doing on the left here. It's just looping max attempts times. If it succeeds, then it will, if it succeeds, then it'll check if it triggered new coverage. If it does, it'll add it to the corpus. Otherwise, it'll just keep looping. And then if it fails, it'll just try another mutator. Yeah. I should note, like, a major limitation of Mutation Engine is that it'll struggle to find bugs or programs that require like a specific sequence of n mutations from some original program that you're mutating off of. Yeah. Okay, cool. I guess I'll also mention that like Hybrid Engine basically just like combines code generation with existing mutators. It's kind of like the high level overview of that. Cool. And then how much more? I think that's more. Okay. Cool. So type system and type inference. So Fuzzily will basically has like this optimization called type inference that improved the effectiveness of like code generators and mutators by reducing the amount of invalid code that gets generated. So it'll infer the types of variables, and then the fuzzer can produce, or I guess by inferring the types of variables, the fuzzer can produce more realistic and valid programs, leading to like more successful fuzzing runs. And yeah, so we can see here, suppose on this one, it doesn't have type inference, and it does b.call function, and it passes an f, where f is just a random variable, not a function. So in our fuzzle here on the right, when we see it'll like load the string, and then it'll get a type error because it tries to call a function when in reality it's just a random variable. Yeah. And then I guess, wait, go back one more? I'll just like say one more. I guess with type inference, or I guess this is the problem that type inference should fix. Yeah, I mean, that wasn't that bad. Cool. And then this is just kind of like the core components of Fuzzily. I'm not going to go over each one, but I think some interesting ones are definitely like the evaluator, which will basically like determine if like a program or sample here. Oh, you're good. It'll just basically determine if a program is interesting according to some metric. So their basic metric is just code coverage. So if the program finds new if it finds new code paths or it finds new edges, then it'll deem that program interesting and add it to the corpus. For our project last semester, we were also trying to like mess around with like what other metrics we could add. So we were playing around with like more like the internal states and like trying to figure out something cool to do with that. And then I guess another interesting one is probably lifter. I should probably look at this more, but I think that one's pretty cool just because it's like the actual translation from the fuzzile to JavaScript. And then all like the mutation engine and like hybrid engine and the mutators are all also pretty cool to look at if you're interested.
Before we go into the next section, I think it's worth just explaining why we're talking about any of this and what we actually did last semester a little bit more. Yeah, it's like a little TLDR. First of all, if this is like boring, I apologize. Yeah, this was also compressed like crazy. This was like a 3-hour presentation from like the start of last semester, where we started this research project and kind of kicked it off with this amazing slideshow and all this stuff. But what we really wanted to do, and what the goal of all of this was to try to find compiler bugs in JavaScript. And the reason any of this matters, and why specifically JavaScript, is every time you load onto a website, most websites are using JavaScript. Most engines themselves actually run JavaScript, right? The website you're running, or the web browser you're using, has its own custom JavaScript compiler and JavaScript interpreter. And a very powerful exploit scenario, right, is somebody logs onto a website, or it goes to your website, and their entire computer's gone, right? In terms of they get hacked, and the way this is actually done. Um, One of the very advanced ways this is done is by actually targeting the JavaScript compilers, right? These are really expensive bugs. These are bugs that when people say, "Hey, I sold a bug for millions of dollars," this is kind of what people are talking about. The full chain, at least, the renderer bugs are probably a good bit less, maybe like 100, 200K. That's the actual compiler. But regardless, it's they're cool. They're really powerful bugs, and there's an entire industry and job market for this. Uh, but yeah, the other thing we actually really wanted to do was there was, if any of you guys remember Sharad from last year, he did a competition called AIXCC. So we kind of wanted to merge both of like the JavaScript fuzzing, attacking compilers with AIXCC. And the idea there was using AI to augment fuzzing and improve fuzzing. And that was like kind of the whole last semester for us, where we were taking this really complicated fuzzer that targets this compiler and improving the fuzzer in very standard ways in terms of, hey, we're getting more information about the compiler through compiler heuristics, like Aleksi was talking about, and improving the fuzzer's execution speed and all the standard stuff. But it was also like, hey, we're making these really complicated AI systems. And part of that was inspired by Trail of Bits as well as Team Atlantis, in terms of their AIXCC systems, and it's kind of why we're talking about this next. But yeah, if any of this interests you, please come to VRig. Yeah, we meet every Wednesday. It's a shameless plug, yeah, but we meet every Wednesday, Thursday, and we do more fun stuff like this. We're currently Monday, Thursday. You're right. Fuck, different days now. But yeah, I don't know. I don't know why I said Wednesday. I'll be honest here. But we're doing allocator security research and looking into designing allocators and doing like a little competition before going back to compiler exploitation. But yeah, really quickly to go over what Trail of Bits' AIXCC system looked like. We had the initial seed generator. So what this would do was it would find and create harnesses as well. And this is all done through AI. So the idea is you throw it into a code base. You have this really complicated code base. You're given a harness before the system actually runs. It's kind of just the format of the competition. But the idea is now, okay, you want to create and generate initial seeds that are useful. You want the fuzzing harness to run. You want to get information on the seeds that you'd actually generated. After that, you want to maybe explore the code base a little bit, and then you want to generate new seeds based off exploring the code base and trying to find bugs. And then you also have an AI system that fully agentically goes and tries to find bugs by itself. But yeah. This is kind of like the overview of how it works. You have start seed in it, load harness in it, initialize task state, context retrieval loop. If we need more context, we'll run our AI system. It can make tool calls, get function, get type definition, cat the file, get callers, batch tools. Then we retrieve the snippets and we give it back to our AI system in order to generate seeds and execute in a sandbox and then save those seeds. But yeah, so the idea is we're essentially allowing AI to autonomously generate input seeds, and then it goes through the code base and also autonomously finds interesting inputs. So the next thing you also have is seed starts seed explorer, which it'll load a target function, go through the function, try to understand the function, and if the function is possibly exploitable or see something interesting inside of that function, it can also generate test cases and inputs to try to exploit that. You're not really exploiting it. I guess that's a misnomer. You're more so trying to just get that initial bug and initial crash from the harness. And then vulnerability discovery is the actual like, hey, let me try letting AI go full on schizophrenic and try to find a bug. Obviously, it's not exactly that. It's a lot smarter. But the idea of vulnerability discovery here is that we're going to go through, let AI analyze the code base and system and try to find bugs and then submit it. Yeah. This was like their main AI system. It's kind of Cam slide. I don't know what he's talking about near the end. I'll be honest. I don't know why there's a Martin Luther. Yeah, what is going on here? Yeah. But really, the idea was, hey, how can AI be included in novel security research, and how can you improve the way modern fuzzers work? Is what two teams kind of did. Which a lot of the other work was also, how can we fully use AI to find bugs? And a lot of companies now are trying to do that. And there's like this kind of global arms race to make these cool AI hack systems to find bugs. But yeah, I think that's it from me. It's the end of our. You have anything to say?
No, I don't think so.
Thank you.
Anyone have any questions, I guess?
Oh yeah, questions. For chance. All right, fair enough.
Yeah. Cool. Thank you.
Thank you. Thank you. Thank you.